Okay, now that we've done basic probability, let's move on to the more complicated version of probability involving multiple events taken in succession. So first off, let's look at a coin toss, only this time let's do 2 coins instead of 1. So what is the sample space for this game? Suppose you flip 2 coins and look down at the 2 coins. What are the possible things you might see? So for this example, you'll have coin 1 and coin 2, and then the full event. So for coin 1, you'll have a head. For coin 2, a head. The full event would be 2 heads. If you have a head for the first coin and a tail for the second, you end up with a head and then a tail. This is different than if the first coin had a tail and the second coin had a head. So that would be a tail and a head. And then if each coin showed a tail, there would be 2 tails. So let's start discussing the sample space. There are 4 total events, and we can abbreviate them to write them more simplistically, which is HH, HT, TH, and TT. Now let's look at some events. What is the probability that both coins show a head? So if you look in the full event column, you'll see that there's only one area where it says head, head, out of 4 possible options. So in that case, there's only 1 out of 4 for the probability of a head, head. Contrast that with at least 1 head showing. If 1 head is showing, that means any of the coins shows a head. So you can either have both of them showing a head, that's at least 1. The first one is a head, or the second one's a head. So you actually have 3 out of 4 possibilities for that event. Now, let's look into rolling dice. So before we did 1 die roll, let's look at what happens when we roll 2. The sample space gets a little more complicated because we have 6 possibilities for each die and any combination with the other. So this is actually the sample space. And for a quick calculation, it's 6 by 6, so there must be 36 events. So let's look at the event summing to 7. So if you look in this grid and you add the dice together, then the sum to 7 is across the diagonal, where it could be 6 plus 1, 5 plus 2, 4 plus 3, or the reverse. In this case, we have a total of 6 possible outcomes that meet the event out of 36 total possible outcomes, which gives us a 1 out of 6 probability of having dice that sum to 7. Let's think about the possibility of a 6 showing. So again, we look to the sample space to try to figure out where are the 6s. We have them if the first one is a 6, and we also have them if the second one is a 6. And if we count all of these individually, we'll have 11 out of 36. Now, you might remember the general addition rule from the first video. Let's put that into play in this example. So again, let's suppose we're looking for at least 1 die showing a 6. So we could pick the first die showing a 6 or the second die showing a 6 and just do each of those probabilities separately. Then we'll get a 6 out of 36 plus a 6 out of 36. But don't forget, we double counted this one, the 6, 6, because both die are 6s in that instance. So there's an overlap. So we're going to subtract that off. So the first event, there were 6 outcomes. The second event, there were 6 outcomes. And the overlap, there's 1 that they both have in common that we need to subtract off. And we'll get 11 out of 36, just like we did in the previous way of computing at least 1 die showing a 6. Now, you might remember from the first video the complement rule. Let's put that into play as well. Suppose we are asking for the probability that no die shows a 6. So we want to get rid of all the 6s that we just calculated and only stay within the inside box here as shown. Now, because we could easily multiply, we can see 5 by 5, it would be 25 out of the 36. So that's a pretty quick way to do it. But let's try using the complement rule anyway. So no die showing a 6 means we get rid of these 2. Since we just calculated it, we know that those sum to 11 out of 36 for the probability. So we can simply subtract that off, since now we want anything else, which will give us the 25 over 36. Now here, let's take a coin and a die as our sample. So we're going to flip a coin and we're going to roll the die. Now, as you can see, we're trying to figure out what events are possible. In the first column, we have just heads and all the possible ways we could roll the die. In the next column, we have all being tail with all of the die. And these are all different events. So the full list of events looks like the following, where H is a simple way to represent head, and the numbers are a simple way to represent the side of the die. So in total, we have 12 possible events. So our sample space has all of these that we can use to calculate our events. Now, suppose we want the probability of getting a head and a 6. So we need to look at all the ways that we can get a head and a 6. Because it says and, both have to happen. Therefore, there's only one in the bottom left corner that's H6. That qualifies as the event. So it's 1 out of 12 is the probability of a head and a 6. Suppose we want a tail and a value greater than 3. So that simplifies it to this side. We're looking at tails. We don't have to worry about heads. And, which means also has to happen, a value greater than 3. So 3 is not greater than 3. So we are looking at T4, T5, and T6, which gives us 3 possibilities out of a total of 12 in the sample. We can also simplify that to 1 over 4. By the way, you could also do this in Excel. You can represent fractions by using that format option that we discussed before when we were talking about relative frequency and when we were talking about entering text data such as 1-10 that defaulted to January. Remember, we can reformat all the cells. So if you wanted to type in a cell equal 3 divided by 12 and put it as a fraction, it'll simplify it to 1 over 4 for you. You could try that out. Now, for this event, we're looking at tails. Again, we're in this column and a value greater than 0. Well, this entire right-hand column is greater than 0. So we have T1, T2, T3, T4, T5, and T6 as all qualifying events, which gives us 6 out of 12, which is simple to see that it is half of our full events. Now, what about getting a head or a value no less than 5? So in order to satisfy this event, we can get a head, and that would satisfy this requirement. And since it's an or, we can automatically include all of those. So H1 through H6 are all included in this event. Now we just need to see if there are any tails that have a value for the die that's no less than 5. And no less than 5 means that it would be 5 or greater. So our possible events are H1 through H6 and also include T5 and T6 since they satisfy the second requirement and there's an or. That gives us a total of 8 over 12, which simplifies to 2 over 3. This brings us to another rule that we can use to help us calculate probabilities more quickly and easily now that we're doing multiple events. So when we're doing multiple events, you should think multiplication rule. Let's see this one in action. What this is saying is if you have two events occurring simultaneously or together, then you can take the probability of one event and you can multiply it by the probability of the next event, giving the first event happened. And the reason that this exists is because if the first event didn't happen, there's no way to get the and with the following event. So for instance, get a head and a 6. Well, first we have to be able to get a head. A head is easily calculated as 1/2. The other requirement is a 6. The probability of getting a 6 is 1/6. So when you multiply these, you get 1/12. Let's do another example. Suppose we talk about the example where we flip a tail and we obtain a value greater than 3. In order to get a tail, that's a 1/2 probability because it's one side of the two-sided coin. And in order to get a value greater than 3, we could either roll a 4, 5, or 6, which is 3/6. When we multiply these events, assuming that they both happen, we'll get 3/12 or reduced 1/4. Now getting a tail and a value greater than 0, the first event is a tail, which is a 1/2, again, because one out of the two sides of a die. Now for the die, it could be anything and it satisfies the requirement. So that would be 6/6, also known as 1. And when you multiply 1/2 by 1, you'll get 1/2. Now suppose we have a head or a value no less than 5. For this one, it becomes a little more complicated because we have that overlap. So now for the or, we have to add up the separate probabilities and then subtract off the overlap, which we can get using the multiplication rule. So for the first event of a head, we have a 1/2. For the second event, no less than 5, which means 5 or 6. That's 2/6 for the die. And then we're going to subtract off the probability of both happening, which is 1/2 times 2/6. With a little bit of work and calculation, we arrive at 8/12, which simplifies to 2/3. Now, these last two examples are going to deal with cards. So if we are being dealt 2 hearts in succession, which means one after the other, what is the probability of such an event? So the first heart we have to calculate is 13/52 because of all of the hearts. But then we get rid of one of these. Let's say we got rid of this ace right here. If you remove that one, because that was the first one we selected, assuming we selected one of these because it's required or we can't do the event, then we only have 12 out of 51 cards remaining because this one no longer exists. This ace is gone. Again, you could pick any one of the hearts to disappear. It would still reduce the total number of cards by 1, as well as the number of hearts available by 1. In contrast, suppose we pick an ace first and then a picture card. Since these two events don't overlap, then we won't lose the second event's numerator, but we still lose it as a card in the deck of cards. So if the first one is an ace, we have one of these 4. So we have 4/52 as our chance of grabbing the first card that we need. And then over here, we have these 12 face cards, or picture cards, if you will, that we can choose from, but we've lost one of the aces in order to arrive at that probability. So therefore, we only have 51 cards left in the deck. When you multiply that out, it'll simplify to 4/221. And that's it for the multiple events. I hope this video was informative, and I look forward to seeing you at the next one, discussing contingency tables, which is where probability and statistics get together at last.